and we'll start on our new stuff. So this week we are moving into the step where we actually start to do some calculation. And we're looking at summarizing data numerically. And we had talked at the very end of last week about dot plots. And in our dot plots, it was basically a number line. So let's say that we have a quiz where we've had scores ranging from 4 to 10. And we just make a number line going from 4 to 10. And we look at students' scores. We start grading these quizzes and we just put dots on the plot. Let's say the first one we grade is an 8. So we put a dot over the 8. The next one maybe a 6. Then another 8. So there's already a dot there. So we stack them up and we just keep scoring the quizzes and putting the scores, putting dots on the plot for those scores. And over time, if this is a normally distributed set of data, we should find a very distinct pattern forming in these dots. And basically what happens, as you see here, and I'll just stop there. If I draw a line through the top dot in each column, I get that bell curve. And when we look at describing that bell curve, let me make another little number line here. Let's take, I'm gonna put a bell curve up here in blue again. If I wanted to describe the, oops, this is in green, but that's okay. If I wanted to describe this bell curve to someone, one of the things I might use is, well, the center of that curve seems to be above 6. So I would say the center is at about 6. Maybe I have another curve. It looks like this. Moved over here. And the green curve and the blue curve are pretty much the same shape. The difference is the center of the blue curve is above the 8. So I can describe these curves. One of the qualities I would describe is the center of the curve, the location of the center of that distribution. And then the second thing that can change, let's compare that green curve again to this new red curve. They both have a center over 6. They have the same center, but the red one is less spread out. So spread, some textbooks use the term dispersion, is the second thing that describes these curves. And so these curves are representing a data distribution. And so we can summarize the distribution of that set of data by quantifying those two quantities, center and spread. So let's look at different measures of center. And I'm going to put up 2 sets of data over here that we're going to use. Our first set of data, I'm just going to label it data set A. And it's going to be 13, 9, 21, 15, and 17. And you're going to note this data set has 5 items in it, so that's n equals 5. The number of items, n is equal to the number of items in the data set. Data set B is going to be 8, 18, 23, 16, 12, and 13. There are 6 items in this set, so n equals 6 for data set B. Now again, n is just one of those things that we use to describe a data set. It is the number of items in that sample. Little n would be a sample. If it was a whole population, we'd use large N or capital N, and that would be the number of items in the whole population. So when we describe our measures of center, the first one we're going to use is the mean. The mean is the mathematical average. This is the one that we've been using since about 2nd or 3rd grade. We add them up and divide by n, by the number that are there. Symbol wise, it would look something like this. That symbol is sigma. That X stands for each individual value. So you add up the X values and divide by N. So for data set A, I have 13 plus 9 is 22, plus 21 is 43, plus 15 is 58, plus 17 is 75, divided by 5, that gives me N equals 15 is my mean there. For data set B, add them up, I have 8 plus 18 is 26, plus 23 is 49, plus 16 is 65, plus 12 is 77, plus 13 is 90 divided by 6, that is also 15. So both of those data sets have the same mean. They both have a mean of 15. So then let's take a look at the second measure of center, which is the median. The median is physically the middle of the data. So to find the median, we actually have to go through a 3-step process. Step 1 is to put the data in order from smallest to largest. So for set A, that's going to be 9, 13, 15, 17, and 21. Step 2 is to find the position of the median. Now this is done using N and the fact that the median is in the middle. So in the middle, half the data would be smaller, half the data would be larger. So that position would be 1/2 or 0.5 times N. So for set A, N is 5, so it's 0.5 times 5 equals 2.5. Since this is a decimal, we round up. So it would be the third number in the list. So then step 3 is to just find the median. We said it was the third number in the list. We come up here, 1, 2, 3, 15 is the median for set A. Now I'm going to pause for a second here. The median for set A is 15. The mean for set A is 15. These are all different ways of measuring the same thing. It's the center of that bell curve. So they should come out to be either the same number or really close to the same number. If they're different, that means there's a little bit of skew in the data. The data is not perfectly normally distributed. Let's look at set B here. So first step is to put them in order. So we have 8, 12, 13, 16, 18, and 23. Find the position. Well, N is 6. So 0.5 times 6 equals 3. Since this is a whole number, in other words, no decimal, that means it is between that and the next position. So that's telling us the median here is between the third and fourth number in the list. So we locate those. 1, 2, 3. The third number is 13. Fourth number is 16. To find out what's between them, we just add them together, 13 plus 16, and divide by 2, giving us 14.5. Well, let's compare this number. 14.5 is really close to the mean of 15 for data set B, but not exactly the same. So since they're really close, this data is approximately normally distributed, but it might have a slight skew, and I'll explain skew in just a minute. The third measure of center that we use a lot is called the mode. The mode is the item that occurs most often. Now you look, neither one of these data sets has any points that occur more than once. So both data set A and B have no mode. There's no number that occurs more than once. The mode is really only useful in one of two situations. One is really large numerical data sets. By really large, I mean you're talking 50 to 100 or more numbers in those data sets. The second place where the mode is useful is in qualitative. Remember, qualitative is that categorical data. Like if I'm asking for your favorite color, there's no number there to calculate a mean or a median of, but you can find which one was selected the most often. So there is a mode for qualitative data, even though there is no mean or median. So that's where the mode is really useful. It's not terribly useful in other things. Then there's one called the mid-range. The mid-range involves the minimum, which is the smallest number in the data set, and the maximum, abbreviated max, which is the largest number. And it's just literally averaging those together. So for set A, the mid-range is what? 9 plus 21 divided by 2, which is going to be 15. Same as our mean and our median for A. For B, it's going to be 8 plus 23 divided by 2. 31 equals 15.5. So that's, again, slightly different from the mean and median, but really close. So this is still approximately normally distributed, just maybe not perfectly normally distributed. So I mentioned that phrase, normally distributed, and the word skew. Let's talk about how those fit together. So if we have a perfect bell curve, perfectly normally distributed data, the highest point of that curve is the number that occurs the most often. That would be the mode. Now I'm just going to switch colors now for other things. The middle, since the bell curve is always symmetrical, the middle is also going to be in that same spot. So the same number is going to be the median. And because they all average out, and they're symmetrical, the mean is going to be the same number as well. So as we saw with data set A back here, all of my measures of center are the same. That's a perfectly symmetrical, normally distributed set of data. It's a bell curve. But what if they're not the same? Well, there's two options there. One is to be skewed to the left. And you see it's skewed left because the left end of the curve is stretched out, and the other would be skewed to the right. And it'll obviously be just the opposite. It's the right end of the curve that's stretched out. The right tail stretched out. And when we have these situations, it changes our relationship with the mean, median, and mode. So the mode is still the most often, so it's still the highest point on the curve. That's in blue in the original drawing, so I'm just going to put it in blue here. The median then will move slightly because there's more numbers on the left side than the right side, so it's going to move slightly to the left for a left skew, slightly to the right for the right skew. And then the mean will move even further because those really large or really small numbers will move it over. So when we look at the data we had back here for set B, the mean was slightly larger than the median, which is telling us possibly a right skew because the mean is bigger than the median. So the question comes out, what is the best measure of center? Now you've probably felt my opinion of the mode. The mode is definitely only useful in certain situations, so it's not the best measure of center. So it comes down to the mean or the median. A lot of people would say the mean because there's something satisfying about it. You're using a formula, adding the numbers up, dividing it out, you're getting that average. And it's something we've done. We're comfortable with it because we've done it from very early on in our math careers. But there's a weakness with it. And I'll demonstrate that weakness. In 1983, University of Virginia advertised that the average starting salary of a graduate, a BS in marketing, actually not marketing, it was communication, sorry, was just under $78,000 a year. Now that's a pretty decent starting salary right now for a communications graduate. Go back to 1983, and in 1983, your average high school teacher was starting out between $16,000 and $18,000 a year. In 1983, $78,000 was a phenomenal starting salary. But what they failed to disclose was that one of the graduates that year was a man named Ralph Sampson. Mr. Sampson was 7 feet 4 inches tall, and was both his junior and senior year of college was the NCAA Men's Basketball Player of the Year. Pretty great athlete. Voted the best basketball player in men's college basketball 2 years in a row. He was drafted first in the NBA draft by the Houston Rockets, had a multi-million-dollar contract that year, but he still graduated with a degree in communications. It takes a lot of $20,000 communication degrees or communication graduates to average out a multi-million-dollar contract to $78,000. In fact, Mr. Sampson was the only one to make more than $33,000 that year. Obviously, the $78,000 was a mean. The median was just under $22,800. Still pretty good, but not phenomenal like the $78,000. Now, $22,000 doesn't sound like much now, but 1983, it was a big deal. So it's what comes down to what we call stability. Really large or really small numbers will affect the mean more than the median. So the median is more stable. And because of that, we tend to use the median as the more reliable measure of center. So that's why they talk about anything that has to do with income. Median is much better. They're talking about median household income. The reason is you can only go down to 0. So there's not really any huge outliers on the lower end, but you can go up to billions of dollars a year, like a Bill Gates or Warren Buffett or any of those. So if we did mean household income, the mean household income is actually over $200,000 a year in the United States. The median is back down in that $40,000 range. So what can we use these measures of center and spread for? Well, let's talk about the measures of spread here next. Getting ahead of myself. So measures of spread talk about how wide or narrow that bell curve is. And the first one is the range. And the range, we talked about the mid-range. We use the same numbers, just in a different way. It's still the maximum and the minimum, the largest number and the smallest number, but we subtract them. So I'll put 2 data sets over here again. Data set A is going to be 13, 9, 21, 15, and 17. Data set B is going to be 9, 10, 15, 21, and 20. Both of them have 5 numbers in them, so n equals 5. Well, if I wanted to calculate the range over here for data set A, looks like it's 21 minus 9, which is going to be a range of 12. For data set B, well, it's also 21 minus 9 for a range of 12. So the range is the same for those. Does that mean they're both equally spread out? Well, let's take a look. One way to evaluate spread is to use a dot plot. So I'm going to drop my number line again. And I'm going to put data set A in red. So we've got 13, 9, 21, 15, and 17. Well, they're kind of evenly spread out along there. That's not bad. Next, I'm going to put data set B in blue. So I've got a 9, a 10, 15, 21, and 20. So if I look at the blue dots compared to the red dots are kind of evenly spaced. The blue dots are way out on the ends. I would say the blue dots are more spread out, but the range is the same for both data sets. The range is not precise enough to distinguish between these two data sets. So we need a more precise measure of spread, and we come up with that with the standard deviation. And along with standard deviation, we should talk about variance. The variance and standard deviation are really the same formula. We just go one step further to get to the standard deviation. In basic statistics like this course, we tend to use the standard deviation more. If you get into more advanced statistics, more advanced processes, you end up using the variance in your calculations more. What the standard deviation measures is the average distance a point is from the center of the data. Now, because the mean and the median should give us the same number if we're approximately normally distributed, we use them interchangeably. So even though the median is a better measure of center, we use the mean in most of our calculations. So to find standard deviation, it is a 6-step process. Step 1 is to find the mean. So for data set A, 13 plus 9 plus 21 plus 15 plus 17 is 75 divided by 5 equals 15. Step 2 is to subtract the mean from each number. So we've got numbers here of 13. 13 minus 15 is -2. We've got 9. 9 minus 15. Oops, don't know what happened there. Let's get back down here. 9 minus 15 is -6. 21. 21 minus 15 is +6. 15. 15 minus 15 is 0. 17. 17 minus 15 is -2. What we have formed here, what we have found in step 2 has a name. Those are called the deviations, or the deviations from mean. That's how far each number is from the mean. If we wanted to double check our calculation, if we added those up, they should add up to 0, and they would right now. Step 3 is to square each deviation. So squared means times itself. So -2 squared would be a +4. -6 squared, -6 times -6 would be 36. 6 squared is also 36. 0 squared is 0, and -2 squared is 4. Or 2 squared should be 4. This should be a +2, not a -2 over here. There, get rid of that negative. There we go. So these numbers, oops, gotta reset here a bit. These numbers also have a name. These are called the squared deviations. Step 4. Find the sum. In other words, add them together. Add them up. Well, if I add those up, I get a total of 80. This 80 has a name as well. It's the sum of the squared deviations. Now, step 5, I'm going to go over here. Step 5 is the tricky part. Divide by n minus 1 if it is a sample, or divide by n if it's a population. Now, we're assuming these are samples for this example. So we're going to divide n equals 5. So n minus 1 equals 4. So we'll divide by 4. So we take that deviation of 80 divided by 4 to get 20. This number here also has a special name. The result we have here at the end of step 5 is the variance. Now we said standard deviation was a 6-step process. So step 6 is to find the square root of the variance. So the square root, remember, looks like this. The square root of 20 is going to be 4. I do this off screen here. 4.472 around it too. That would give us that the standard deviation. Now, I could do the same for set B and show you that it's larger, but what I'm going to do is we're going to actually jump to the calculator and show how to find many of these values in the calculator. So what we're going to go through stat. In the edit menu, we're going to select edit. Takes us to our list. So I'm going to arrow up to the top of each list. Notice I'm highlighting L2. I'm going to hit clear and enter to clear out that list. I'll go over to L1, arrow all the way up to the top to highlight L1 and do clear and enter to clear out that list. So now I'm going to use set B, which is 9, 10, 15, 20, and 21. Those are the numbers in data set B. I'm going to do second and quit to get out of here. And now I'm going to calculate what's called the one variable statistics. I go stat, I go over to calc, and I select one variable stats, option 1. My list is L1. If it's not L1, I do second and 1 to put L1 in there. My frequency, I always leave that blank, and then I hit calculate. And notice it says my mean is 15. This sum of the x means the x add up to 75. Sum of the x squared is not important. Now, this next one, we have to be careful. Sx is the standard deviation if it's a sample. This one here is sigma x. That's the standard deviation if it's a population. So the symbol for a standard deviation is different depending on whether it's a population or a sample. S is the symbol if it's a sample. Sigma is the symbol if it's a population. So this is a sample, so it's 5.523 is the standard deviation. Notice that is bigger, or way bigger, than the standard deviation for set A. I'll put that up here as 4.472. So we can see set B is more spread out than set A. And the standard deviation distinguishes that. It's precise enough to distinguish it. Some notation I want to make sure we get down here. Notation symbols, I should say. Let's distinguish between a population and a sample. So the size of population, it's capital N. For a sample, it's little n. For the mean, for a population, it is the Greek letter mu is the mean of the population. For a sample, we use x with a little bar over it. That bar stands for mean or average value of x. And then for standard deviation, the population, it is that sigma, looks like that. And for a sample, it is simply S. So now let's look at what do these centers and spreads tell us about the population. Well, one thing it tells us is the amount of data that is in each portion of the bell curve. The empirical rule says that we can divide the bell curve, the normal curve, into standard deviation ranges, starting at the center. So what does that mean? So here's our curve. We start at the center of the curve right here. How do we define the center? Well, the mean or the median. We tend to use the mean when we're calculating. Then we go out in steps of a standard deviation in each direction. And usually we go 3 steps in each direction. So each of these steps is a standard deviation. So this point here would be -1 standard deviation, or 1 standard deviation less than the mean. This would be -2 standard deviations, 2 standard deviations less than the mean. This here, -3 standard deviations. Going the other way, this would be +1 standard deviation, +2 standard deviations, and +3 standard deviations, 3 standard deviations above the mean. And the percents that are important here if we go 1 standard deviation on each side of the mean, we expect 68% of the data to fall in that range. If we go 2 standard deviations on each side of the mean, we expect 95% of the data to fall in that range. And if we go 3 standard deviations on either side of the mean, we expect 99.7%, or almost all of the data to fall in that range. Well, what does that mean? Well, let's actually find a data set where we have a mean and standard deviation. Let's look at home prices. And let's say in your area for an average 3-bedroom, 2-bathroom home, the mean price is, of course, it's gone way up now. Now let's go 280,000 with a standard deviation of 60,000. So what that means is the middle of this curve, I'm just going to put 280 in there. I'm going to drop the 1,000 off of it. It's 280,000. Going to the left, we would subtract the standard deviation. The standard deviation is 60,000. So 280 minus 60 would be 220. Minus another 60 would be 160. Minus another 60 would be 100. Going the other way, 280 plus 60 would be 340. Plus another 60 would be 400,000. And plus another 60 would be 460,000. So what do these say? Well, in your area, if I were looking at homes, I would expect 95% of them. That is not a very good color. Let me fix that. I would expect 95% to be between $160,000 and $400,000. I would expect 68% of them to be between $220,000 and $340,000, and so on. So this kind of gives us an idea of where we expect what percent of the data we expect to be between certain values. Now, this only applies if the data is normally or approximately normally distributed. So what if the data isn't normally distributed? Well, the empirical rule doesn't apply anymore. So we have to use something called Chebyshev's theorem. Chebyshev's theorem says for any data distribution, for k greater than 1, the percent of the data within k standard deviations of each side of the mean is 1 minus 1 over k squared. So what does that mean? Well, let's say we have a data set that's not normally distributed. Let's say it has a mean of 40 and a standard deviation of 8. Let's find the percent between 24 and 56. Well, first I need to find how many standard deviations that is. Well, if the center of my data is 40, going 1 standard deviation would be subtracting 8, that'd be 32. Another standard deviation would be 24. So 24 is 2 standard deviations below the mean. Let's check to make sure we've gone the same distance in the other direction. So 1 standard deviation adding on to the other side would be 48. Another one plus another 8 would be 56. That's plus 2 standard deviations. So we are 2 standard deviations on either side of the mean, which is telling us that k equals 2. That's how many standard deviations we've gone around the mean. So then our formula will be 1 minus 1 over 2 squared. Well, 2 squared is 4, so this is 1 minus 1/4, which is 3/4, or 0.75, which is, of course, 75%. So for any data distribution, we expect at least 75% of the data will be between or within 2 standard deviations of the mean. So that's the Chebyshev's rule, which follows the empirical rule, but Chebyshev's rule is for any set of data. The empirical rule is only for normally distributed. Now, normally distributed data follows Chebyshev's theorem because it says at least 75%. Well, 95% is at least 75%. So it's true, at least 75% is within 2 standard deviations. It's just the empirical rule goes further and says we can, if it's normally distributed, we have even greater values that are closer to the center of the curve. So let's talk about measures of position. And the main measure of position we're going to look at is percentiles. A percentile is the percent of the data that is smaller than a given number. So let's look at a data set. Now, one of the steps in percentiles is to put the data in order. So I am going to start out with this data in order. So there I have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N equals 10. This is my size of that set of data. Now, if I want to find the number in a given percentile, in other words, I'm finding locate that percentile. What I'm going to do is I'm going to find the position again. And just like finding the median, I take the percentile times n. So my example here, let's find the 80th percentile. Well, 0.8 is the 80% times n of 10 gives me 8. So that's a whole number. So it is between the 8th and 9th number in the list. Well, the 8th number in the list is 27. The 9th number is 30. So the 80th percentile is between 27 and 30. 27 plus 30 divided by 2 gives me 28.5. This is my 80th percentile. I might ask you to find the 25th percentile. So again, we do the location 0.25 times n of 10 gives me 2.5. That's a decimal, so I round up to the third location. Looking at my set of numbers up there, the third number is 18. So the 25th percentile is 18. Now you might notice the median was found by doing 0.5 times n. The median is just equal to the 50th percentile. If I want to find the percentile of a number, well, then I use a formula. That formula is the number that are smaller plus 1/2 times the number that are equal divided by the total, divided by n. So let's say I want to find the percentile of 23. So if I look up in my list up there, here's 23. There's 1, 2, 3, 4, 5, 6 numbers smaller. So that's 6 plus 1/2 times, there's only one number equal to 23. And we'll divide that by 10. Well, 1/2 times 1 is 1/2. 6 plus 1/2 is 6.5. Divided by 10 equals 0.65. That is the 65th percentile. If I want to find the percentile of 20, well, if I look up there, there's 3 that are smaller, plus 1/2 times, well, there are 2 that are equal, divided by 10. Well, 1/2 times 2 is 1, 3 plus 1 is 4, so 4 divided by 10 is 0.4. This is the 40th percentile. So those percentiles are pretty simple to work with. You've all seen them. If you have children, you might be told, oh, your child's height is in the 65th percentile. Now, 65th percentile doesn't sound very good, but remember, average is the 50th percentile. So anything above 50th percentile is above average. When we're breaking down data and representing its distribution, we often use something called quartiles. The quartiles divide the data into 4 equal pieces. Now, by equal pieces, I mean same number of data points in each piece. So the number range might be different, but the number of data points in each range will be the same. Now, if you think about it, when if I have to cut a piece of wood or whatever into 4 pieces, it only takes 3 cuts. So there are only 3 quartiles. There's 3 boundaries to cut it into 4 pieces. So the first quartile, or the lower quartile, abbreviated often Q1, is just equal to the 25th percentile. The middle, the second quartile, which isn't even ever called the second quartile because it's just the median, is equal to the 50th percentile. And then the third quartile, or the upper quartile, abbreviated Q3, is the 75th percentile. And again, the calculator will do this for us. Is somebody in the chat? Cool. Let's look at the data set we had in the calculator before. Let's go back to the calculator. So here I have the mean and I have the standard deviation for a sample and population. But notice I can keep going down. If I arrow down, I have the minimum. The first quartile is 9.5, median of 15, third quartile of 20.5, max of 21. These 5 numbers here make up what we call the 5-number summary. That would be the minimum, the first quartile, the median, the third quartile, and the maximum. So for this data set that we had in the calculator, that was 9, 9.5, 15, 20.5, and 21. So there is the 5-number summary. And that is used to make something called a box plot or a box and whisker plot. Similar to a dot plot, the box plot uses a number line. It goes from the smallest number up to the largest number. Now, Excel has an add-in function in the data analysis tool pack that does box plots, but it does not do them correctly. It does a very poor job of it. So I'm okay if you just use the draw tools in Microsoft Word, just like I'm doing here on screen to sketch out the box plots. So I'm going to start with the quartiles. Q1 is 9.5. That's going to be right here. So I'll put a vertical line at 9.5. The median's at 15. So I'll put a vertical line at 15. Q3 is at 20.5. So I'll put a vertical line there. And then what I'm going to do is I'm going to connect the quartiles to each other. And you can see that forms a box. And then I do a whisker out to the minimum, to 9. So from 9 into the first quartile, I do that whisker. And from the maximum of 20, notice those whiskers are very short. What this is saying is the data is the bigger the section of the graph is. And there are 4 distinct sections of the box plot. This is section 1 is the whisker. Section 2 is this part of the box. Section 3 is this part of the box, and section 4 is this other whisker. The bigger that section is, the more spread out the data points are in that section. Now, if we go back here a couple of slides, remember when we did this data set, that was the one in blue here. We said it was way spread out. The data was more out on the ends and there was nothing in the middle. That's exactly what our box plot is showing us here. There's nothing in the middle. There's very few points in the middle, so we have to go way out to get a fourth of the data points. But there's a lot of points out on the whiskers, so the whiskers can be very short and still have 1/4 of the data points. Now, if it were normally distributed, it would look very different. Normally distributed data would be symmetrical for 1, so the 2 sides of the boxes would be the same. And the whiskers would be longer than this section of the box, like that. Now, I didn't get my box lined up really well. Let me see if I can adjust that. There we go. So that would be the box plot of an approximately normally distributed set of data. So that's one of the ways we can evaluate whether a set of data is pretty close to normally distributed, is to look at the box plot. again, to make sure the whisker here is longer than this half of the box. Of course, remember, we've already discussed the one where the mean, median, and mode are the same value. Okay, so that is our basics for the night. I want to now talk about finding measures for grouped data. And to do that, I'm actually going to open up Excel, which means I got Excel open on my desktop here. Give me just a second. Coming up a little slow, so give me just a minute and we'll have Excel up. So what we're going to look at is we're going to look at the number of classes that students are taking. We're going to take a sample and look at how many classes those students are taking in that sample. So let's share my Excel document here. So we're going to start out with number of classes being taken. And remember, if there's 0, they're not a student. So we're going to start out at 2. And let's say nobody in our sample had more than 5. The frequency, let's say we've got 9 that took 1 class, 14 took 2, 23 taking 3, 16 taking 4, and 8 taking 5 classes. To find the median, we need to first find n, the total number. So we'll find total here. I just add up my frequencies. There's 70. So the median is between the 35th and 36th number. How did I get that? Well, 70.5 times 70 is 35, and that's a whole number. So it's between that one and the next. So the 35th and 36th. Well, to find that, let's find the cumulative frequency. So this is 9. 9 plus 14 would be 23. 23 plus 23 would be 46. I could actually stop there, but let's go ahead and finish it out. 62 and 70. The 35th and 36th data points are between, well, the 2 would go up to the 23rd data point. The 3s go up to the 46th data point. Now remember, there's 23 3s. What this is really saying is we have 1, 1, 1, 1, 1, 9 1s, and then 14 2s, and then 23 3s. So the 35th and 36th number are both going to be 3s. So the median here is going to be 3. The mean is a little bit tougher to find. To find the mean, I start out by doing the number times its frequency. So here, number times frequency. So it's going to be this times its frequency. And I do that for each number. So I'm going to fill that down. And I find the sum of those. The mean is then that sum divided by the total frequency, by n. So here that'd be 210 divided by 70 gives us a mean of 3. So there's our mean, there's our median and mean. Both of them came out to 3 for this data set. The mode would be easy to find. It's just going to be the largest frequency. Largest frequency is 3 because there's 23 3s. So mean, median, mode are all the same number. Now let's look at the standard deviation. This one's going to take some work. Remember, we find the mean. We've already done that. 2 is subtract the mean from each number. So here we're going to do x minus the mean. So that'll be this number here. Oops, my equals in. this number here minus the 3 of the mean, or put that all the way down. We have to square that. So equals this number squared. And we'll do that for all of them. Now, the thing is, this number here, this square doesn't occur just once. There's 9 ones, so it occurs, the 4 occurs 9 times, the 1 occurs 14 times. There's 23 ones, so that, or 23 threes, so the 0 occurs 23 times, and on down the list. So we have to take that square times the frequency to account that there's more than one of each. So that's this times the frequency over here. Make sure you use the regular frequency, not the cumulative. We get those. And now we add those up. We get 98. And then, of course, we divide by n minus 1. So we divide by 69, which is going to give us, go off screen to do 98 divided by 69, 1.420. That is our standard deviation for that set of numbers. So we can find measures of center and spread for group data as well. I'm going to stop there. Anybody have any questions? Okay, I'm going to go ahead and shut off the recording.